Alright, so today I'm going to be explaining this important paper with the title Structure-Aware Random Fourier Kernel for Graphs. This NOIPS paper in 2021. Gaussian processes. By the way, the generalization of Gaussian processes is neural processes, because you can also learn the mean and covariance. So we call it neural process. But here is the Gaussian process. Gaussian process define distributions over functions, and their generalization capabilities depend heavily on the choice of kernels. In this paper, we propose a novel structure-aware random Fourier kernel for Gaussian processes that brings several benefits when modeling graph structured data. First, this SRF, structure-aware random feature, this SRF kernel, is defined with a spectral distribution based on Fourier duality given by the Büchner theorem, transforming the kernel learning problem to a distribution inference problem. Second, this structure-aware random Fourier kernel admits a random Fourier feature formulation that makes the kernel scalable for optimization. Third, this SRF kernel enables to leverage geometric structures by taking subgraphs as input. Even that paper, equivariant graph neural network, they use subgraph. So subgraph is the elementary, let's say the primitive unit that we need to care about in the context of graphs. So to effectively optimize Gaussian processes with SRF kernel, we develop a variational expectation maximization algorithm which alternates between an inference procedure and a learning procedure. So Gaussian process models for graph structured data have been widely studied. They have been proposed for different learning tasks such as object classification, link prediction, user profiling, graph classification, even uncertainty analysis. But the kernels applied in these methods are feature-based, which may be suboptimal in capturing the local structural smoothness in graph data. In contrast, the structure-based Laplacian kernels capture object similarities based on the geometric structures. However, they rarely utilize the rich object features and may not be capable enough to model the complicated functions over large-scale graphs. So our GP-SRF differs. First, SRF kernel is both feature-based and structure-aware. The second one, the random Fourier feature formulation of that enables efficient optimization. So a Gaussian process defines a distribution in a function space, which assumes that the marginal distribution of function values of any finite inputs is Gaussian. Specifically, a Gaussian process places prior distribution over functions. Now, the Fourier duality between the kernel and the spectral distribution enables to define an explicit feature mapping function. And also, they have background on graph neural networks here. Now, this is a structure-aware random Fourier kernel. We propose a novel structure-aware random Fourier kernel. To efficiently infer the spectral distribution, it is convenient to define spectral distribution as reparametrizable distributions such as Gaussians. However, they may not be rich enough to represent expressive kernels. For examples, the unimodal parametrizable distributions are difficult to reconstruct the kernels whose spectral distributions are multimodal. To obtain a flexible and expressive kernel for the complicated functions over graph structured data, we define the spectral distribution in a hierarchical Bayesian manner. So we can obtain samples from conditional distribution by drawing this auxiliary variable u, and we obtain omega as a deterministic function of that sample u. Now, despite the RF kernel is expressive and scalable, it is still feature-based and may be inefficient in capturing the local geometric structure in graphs. To address this issue, we propose a structure-aware random Fourier kernel, which is RF kernel that takes L-hop subgraphs centered at the objects as inputs. And specifically, the SRF kernel between two objects is like this. So this is the SRF kernel between the two objects. We define a vector-valued stochastic process over graph structured data, where D is the output dimension. The joint probability of our graph Gaussian process is defined like this. And F represents the labels and functions of y is the label, f is the function values of all objects, and the likelihood function in our model is defined with a softmax function. E sub c is the indicator vector, with the cis element being 1 and the remainder 0. The stochastic function is assumed to follow a Gaussian process prior. By using the proposed SRF kernel, this Gaussian process prior is this. Now we propose to approximate the basis function psi with random Fourier feature maps. With random Fourier feature formulation, the joint distribution is equivalently represented like this. And y represents the labels of all objects, and we omit the dependence of the network structure E for clarity. Now, to make predictions for the unlabeled objects, we need to infer the posterior, which is intractable for our multi-classification model. We develop a variational expectation maximization algorithm. Specifically, we introduce a variational distributions over latent variables Q. The log likelihood of the observations can be written like this. So this L is just the evidence lower bound that you have seen several times. Now, inference. In the inference procedure, the expectation step, the model estimates true posteriors over latent variables. And we fix P sub theta and update the variational distributions to approximate the true posteriors. We further define variational distributions over latent variables, A, as Gaussian distributions. And with variational parameters at step T are optimized like this. In the maximization step, which is the learning procedure, the goal is to update the generative model parameter theta. So we first pre-train the inference model Q sub phi for a few steps, and then perform the alternate optimization between inference and learning. And you see the 1D regression results for the proposed RF kernel on the left, and compared with the RBF kernel and deep kernel on the right. And you can see different data sets like Cora sites here. You can see the classification accuracies of Gaussian process, graph neural network, and the proposed method here that you see some improvements.